Hi, everyone. Can you all hear me? All right. I think it's time we'll just get started here. Hi, my name is Dave Bechberger, and we're here today to talk to give my talk about Skeptics' Guide to Graph Databases. But before I start, I kind of wanted to ask a little bit of a question. So, who here in the audience has heard about what a graph database is, or heard of the term? Excellent. So, most of you. How many of you have actually used one? Oh, that's good. I gave this talk a similar talk last year, and there was 2. So now we're up to about 10 or 15. How many of you actually put something into production with one? Okay, we're down to about 4. How many of you actually put it into production successfully? Yeah, we're down to a couple. So that's sort of what the whole premise of this talk is, to kind of walk through the process of what it actually takes to make a graph database implementation successful. So a little bit about myself before we get started. So I've been doing software development for about 20 years. Every time I say that, it starts to make me feel older and older. It's actually a little more than 20 years now, but I don't want to admit how long. And I've done everything. I've done a little bit of everything. I started out, my actual first job was to build embedded C programs on top of DOS. And I've done everything there through building out high performance websites. Most recently, I've been focused on big data problems, specifically around building high performance, low latency data platforms. And a lot of times, at least part of those data platforms has been leveraging a graph database. Currently, I am a solutions architect at DataStax in their global graph practice. If you're not familiar with who DataStax is, we are the Apache Cassandra people. We have our own distribution of Cassandra that integrates search, analytics, and then graph on top of it, which is why I'm part of the global graph practice there. I'm also the co-author of an upcoming book by Manning called Graph Databases in Action. And if you want, that's my Twitter handle up in the corner. If you tweet out during this presentation, I have 5 free copies I'll give away at the end. Doesn't have to be nice, but I would prefer it be nice. So what are we going to talk about? Well, we're going to talk about what graph databases are, just so everybody has a little bit of a level set. It seems like most people at least heard of them, which is great. And then why you should care about them, why they're actually useful in some cases and not in others. Then when should you use one? Because that's the biggest challenge I see when I work with people is they try to use a graph database for the wrong use case, and it just doesn't end up working. Then you can learn from my mistakes. As I said, I've been working with graph databases for about 4 or 5 years now. I've made a lot of the mistakes that you're going to make when you start, so learn from them. Try not to repeat the same problems I did. And then last, we're going to talk a little bit about how to make a successful project and how to actually make that project you're working on successful, or to know if it's not going to be successful early on. So what's a graph database? Graph database is a type of NoSQL database that's built on top of graph theory. So graph theory, if you've ever taken a discrete mathematics course, you've probably heard about the 7 bridges of Koenigsberg problem. Well, what that really comes down to is graph theory basically it gives a mathematical construct to how to describe entities and the relationships between them. Entities they describe as vertexes, which the plural is vertices or vertexes. It's actually both are correct, depending on who you ask. And they're represented most frequently by these circles. And edges represent the relationships between vertices, and they're represented by the lines. So you'll see that throughout this. And really what graph databases are all about, they're all about handling highly connected data types. We'll talk about some examples here coming up, but really they handle those highly connected data types in ways that allow you to get insights into what you're working into your data that you can't get using other technologies. So where do they fit? When I think about databases, I think about databases as kind of a spectrum of data complexity. There's a spectrum of data complexity from very simple data to very complex data. And there's different databases and data stores out there that work with each type very, very well. Simplest one is key value store. We've all probably used these. A lot of times you use something like this for a cache. In a key value store, really, this is your Reacts, your Redises, your DynamoDBs. They're very simple databases. There's a key and a value. There's no real relationships amongst those things. Each one is atomic unto itself, I should say. You want to get a little bit more complex data, you get wide column stores. These are column-oriented databases. This is like a Cassandra, a Google Bigtable, an Apache HBase, if you're familiar with those. And these basically, you really think of them as a single database, a single table in like a relational database. They usually have rows and columns, but there's no ability to join data across rows, no ability to really do any of the more complex connectiveness that you get with other data stores. But they are connected in as much as the data in a single row is connected to each other. You get a little bit more complex, you start getting document databases. This is your MongoDBs, your Azure Document DBs, Couchbases, your CouchDBs, things of that nature. And this starts having some connectedness in your data but that connectedness is all within one atomic document. Anybody here has probably used it. If they used any NoSQL data store, this is probably the one you've most likely used. And they're very, very useful. But what they aren't really great at is being able to connect multiple documents together. While most of them have the ability to potentially join data, that join at best is pretty weak on something like an ID, and it doesn't enforce any sort of referential integrity or anything like that. Then we get to what everybody here has probably done most of their careers is relational databases. Relational databases, tables, columns, foreign keys, this is what probably 95% of the world runs on, is the relational database paradigm. But the thing I find funny about relational databases is even though it has relations in the name, it's actually pretty poor at being able to represent relations in the data. And I say that because the only way you can really represent relations in a data is to link together you can link together tables via foreign key. While that seems great, it's a pretty weak association because that relationship can't really add any value to that connection in and of itself. It's a pretty anemic thing because it's just a name. You can't add any semantic value. That relationship can't have any connectedness to it, which is why when you get down to those sorts of things, you end up with bridge tables and link tables inside your relational database to really try and represent those sorts of rich parts of a relationship that relational databases don't handle. And that brings us to graph databases. Graph databases are all about handling the most complex interconnected data that exists out in the thing. Why is that? Well, that's because graphs are all built on relationships. The essence of a graph from both graph theory and in the graph database world is about relationships and the connectedness of your data. You'll hear me say this many times, but the one kind of major thing that a graph database gives you, or to know if you want to use a graph database, is if the connections between your data are as important or more important than the data itself, that's a really strong use case for a graph database. So what do graph databases look like? Well, when you start with them, they look like this. They look like any other conceptual data model you go build. This is actually a conceptual data model for a Twitter. You have a user at the center. That tweet has links to it. They have hashtags, there's sources, there's media, and they're all interconnected with one another. And when you put it into a graph database, it looks like this. This is actually a real live, not alive, I should say. It's a picture of a graph database that stored actual Twitter data in it. And what you see on the right, I think it's the right, the line one, I'm sorry, my right and my left are not a strength of mine, is what the schema looks like. One of the things you'll really notice about graph databases that's really different than other databases is they do a much better job of representing your conceptual model in a way that looks very similar in both the database and in the real world. So I should say they represent real world connections much better than other things because the database schema looks very much like the conceptual model. So the other reason we're here to talk about this is graph is a hot trend. This slide, I've used this same graphic. It's from dbengines.com for a couple of different presentations, but every single time that line just keeps going up and up. And that line represents the popularity change of graph databases. Since 2014, graph databases have been the most popular trend in databases out there. What I would say in the past couple of years and really in the past year, what I've seen isn't so much that people are interested in graph databases, it's that enterprises are interested in graph databases. And enterprises are starting to put significant resources around projects that are using graph databases and around those technologies as key centerpieces for their platforms moving forward. But it is all just hype, because the hype is strong with this one. Especially if you've been around and you've heard about graph databases the past few years, graph databases are the perfect solution to every database problem out there. You should just use them for everything. No. I think we can all imagine, all can agree that there isn't one tool to solve every type of problem out there in the world. But that's kind of what graph databases have been portrayed as. If you do much research out there, you'll come across this statement: everything is a graph. Well, it's probably true. Everything in the world can probably be represented as a graph because everything is really about things and connections between things. But what really is missing from this statement when you start talking about it from a technical perspective is just because it's a graph doesn't mean you should use a graph to solve it. Graphs are great for certain problems, and you can use them to solve most problems, but there are usually better technologies for a lot of problems. Like I said, I work in graph consulting, and I probably, most of the time, probably 9 times out of 10, I work with customers to tell them not to use a graph database to solve their problem. It was actually pretty rare. I was with a customer last week, and I actually got to tell them to use a graph to solve their problem, and it was kind of a win. It was something that doesn't happen too often. So why graphs? Well, without even telling you what this graph is representing, everyone in this room can probably start seeing patterns in this graph and seeing how the connections between things start showing interesting insight into what's going on. This data specifically is actually, this graphic was made by a colleague and actually my boss, Dr. Denise Gosnell. What it shows is the Medicare data for the United States, so some of the federal healthcare spending. And and the vertices represent doctors. The size of the vertice represents how much a doctor was paid, and the connections the edges, represent patients that were shared in common between doctors. So even without actually having known that, you probably started seeing patterns. You probably started seeing that there was a lot of shared patients between New York and Florida, and New York and LA. And if you know anything about the US, that makes a lot of sense as far as, there's a lot of people that winter in Florida that are from New York. So, but what you also probably noticed is that there seems to be an anomaly down there in southern Florida. Those doctors seem to be getting paid a lot more than everybody else. Well, they were. This ended up being part of, I think it was about $1 billion Medicare scam. One doctor, I don't remember whether it was $20 or $30 million, but in a single year, he billed Medicare for $20 or $30 million, which is probably significantly more than he actually treated patients for. So this is just an example of this data was, I'm sure, in a relational database somewhere. But putting it into a graph allowed these sort of insights to come to the forefront that weren't necessarily easily seen looking at it in a columnar form. Rows and columns aren't necessarily going to show this sort of thing. So this is an example. And when I kind of think about graphs, I kind of think about them in 2 ways. I think of graphs, they do 2 things very well. The first one is they help us solve certain problems that we can solve with existing technologies better. And the second one is they help us solve problems that we can't necessarily solve with existing technologies. And we'll go through a few examples. But kind of before we do that, I wanted to talk a little bit about some good graph use cases. So graph use cases. If you go out on the web, you'll find there's a litany of different graph use cases people will talk about. First one I kind of wanted to talk about, and something I've worked with specifically, is fraud or anomaly detection. So by anomaly detection, maybe this is something like a network intrusion system. Well, fraud and anomaly detection uses kind of a feature of graphs and graph databases, which really comes down to pattern recognition. One of the strengths of a graph database is the ability to look at patterns in data and use those patterns to basically find anomalies. For example, we looked back at that last slide. Basically, we were able to all pretty quickly and easily process that there was an anomaly going on there in southern Florida, and that there were some other anomalies as far as how connections were. And that's something that a graph works very well to do. The second use case that we see a lot of is knowledge graphs. Knowledge graphs, it's kind of a loaded term. There's been a variety of different ones out there. But they kind of fall into 2 buckets that I think of. I kind of think of them as like an old school knowledge graph and a new school knowledge graph. So the old school knowledge graph is really one that's been around for quite a while, and it really is all about building out a semantic understanding of a domain. So really building out connections between, maybe you're a book publisher and you want to put all the words from your books into a knowledge graph and then link them together in ways to find out they're connected, and then to actually be able to infer new connections between things based on articles that you've published or something like that. That's kind of the old, what I think of as the old one. That one's been around for a long time, and that one's kind of had the knowledge graph tag for many years. What's come up recently in the past few years is what I think of as the new school knowledge graph, which is basically, it's all about collapsing data silos inside of an enterprise. So let's say you're a enterprise and you have, maybe you're a retail outlet and you have a store, you have an in-store experience, an online experience, a phone customer support, and an email customer support. And each of those things probably stores data about the interactions that a customer has in separate databases. If you're a customer support representative, when somebody calls in, wouldn't it be very nice to be able to see every interaction that customer has had with you, so you're able to easily and quickly customize their personal experience? If you know they've already tried these 3 steps, you don't want to necessarily tell them to try the same 3 steps to resolve a problem. Well, that's really what I kind of think of as a new school customer or knowledge graph. And that's actually an example of one of our most common use cases. We call it a customer 360. And it's really all about being able to quickly and accurately personalize the experience by taking those data silos and connecting them together. We don't necessarily bring in the data, but we connect them together. We're not necessarily a system of record for that information, but we bring in that data and give applications and customers the ability to or applications and people the ability to quickly see that holistic view of a customer to really create business value by driving a better user experience, which is really in the end what most applications are all about, is making that customer experience seamless. Recommendation engines. Recommendation engines are a bit of an interesting one. And I say they're a bit of an interesting one because they're one that's often touted as a great graph use case. My experience is not really. They work. You can build a recommendation engine using a graph, and as long as you don't have a lot of products or a lot of people, it tends to work very well. My experience is they don't tend to scale as well as one would really hope. There's usually better options out there by doing something. Maybe you need to put some machine learning on it to pre-generate recommendations for different products or for different cohorts of people in order to do it. But trying to do it in real time tends to not scale as well as everybody kind of hyped up that it would. Network and asset monitoring. Network and asset monitoring drives to another one of the really fundamental features of graph databases, which is what's known as an unbounded hierarchy. So you have a network. That network contains, or you have a network and you want to basically find single points of failure in your network. So if you use a graph to model this, you have to think about it. Well, you have a network switch. Well, that's connected to, I don't know, a number of different other switches that are connected to a number of different other switches, another of other switches, down to an unknown number. So that is a really complex problem to try and model because you don't know how many levels deep it goes and you don't know how wide each of those levels are. So if you wanted to do that in something like a SQL Server database and you wanted to find, okay, if this router fails, give me a list of everything else that's going to fail. That'd be a really hard and complex recursive query you'd have to write on a graph data or on a SQL Server database to actually make that happen. On the other hand, that's the sort of thing based on some of the data structures that graph databases use, which we'll talk about here in a few minutes, that actually that graph databases are optimized to answer those sorts of questions. I worked in a previous life. I actually worked at a company that did family trees. We built out a family tree set. I was a chief software architect for them. And we used a graph database to basically model our family trees. And it was exactly this unbounded hierarchy because, we would have people that would have family trees that would have 2 people in them or 1 person in them. We had one person that had 250,000 people in their family tree. So it was really hard to give any sort of predictable analytics or predictable time out of our SQL Server database to be able to answer those sort of things. We were able to, by optimizing it to use a graph, we were able to take the times from basically seconds to timeouts to load those graphs, to load those family trees, down to sub-second to a few seconds, depending on the size of the trees. Identity and access management. This is one that when I started working in graph databases, it didn't make any sense to me why you would want to use something like a graph to model an identity and access management sort of problem. But if you start to think about it, what is an identity and access management problem? So let's say I want to find out who has permissions on a folder. Well, to find out who has permissions on a folder, I have to go find out every potential group that has permissions on a folder, everybody in that group, and then every other overlaying permission those people have potentially on that folder, because you might have been given access in a group and then denied access as a specific user. Trying to build out that graph and be able to quickly and easily figure out who has access to what is actually a graph use case we're seeing more and more. Social networks. Social networks are probably like the classic graph use case. This is your LinkedIns, your Facebooks. This is, I want to find people that follow, people that followed me also followed this person, or, if you know this person, you might know this person. I think this one we've probably all seen, and we're probably all on Twitter and or LinkedIn. So we've probably all seen this problem in real life and in real use. And the last one I wanted to touch on was machine learning. Machine learning is a very interesting graph use case because, I'm not a machine learning expert, so I may not. This one statement may be not completely correct, but as far as I know, there isn't a machine learning algorithm out there, at least none of the common ones, that takes a graph as an input. The irony being, if you look at a lot of them, especially something like a neural network, what it's doing under the covers is it's building out a graph as part of its model that it does. But where machine learning and graphs really do start to overlay is when you can start using some of the features of the graph to be able to add them as input parameters into a feature set. So maybe you want to use something that there's a concept called a triangle count that shows how similar things are, or the distance between two items, things like that. You can use those as input features into a feature set for machine learning. And the other one we see is the ability graphs have to be able to do unsupervised classification based on structure. And using within graphs, you can do things that help find things like clusters of data or influence of data based on how that specific vertex is associated with other vertexes in the graph. And you can use those as inputs to machine learning. So what are these that all these use cases have in common? Well, the first thing really comes down to flexibility. One of the things that graph databases are very good at is being able to work with your data in a flexible manner. All of these use cases, if you really think about it, require some level of flexibility, not only with the data that's stored, but how you look at the data and how you query the data. And the other thing, you'll see it here again, connections. Each of these use cases really, to the heart of it, get down to how the data is connected more than the data itself. But if you're a skeptic, and you're a skeptic like I am, you say, I can do all that stuff in SQL. I've been doing this stuff in SQL for years. You know, I always like this analogy of, you know, if the only tool is a hammer, everything looks like a nail. This, kind of, you know, the relational database is that hammer, and in most cases, it does just fine. But there's two specific use cases here I kind of wanted to call out that where graph databases are definitely work better than a relational database. And this kind of comes back to that and what I said initially, where there's two real things I like to think about in graph databases, is being able to do something another tool does better and being able to do something another tool can't really do. And on the one where we're going to talk a little bit about where it can do graph databases work better than other tools is recursive queries. I mean, recursive queries, I don't know how many people here have ever had to write recursive CTEs in SQL Server. How many people actually like writing recursive CTEs in SQL Server? Yeah. If you've never had to do it, you're very lucky. I find them very complicated to get correct. They end up being very hard to maintain, and your DBAs are probably not going to be your best fans if you have to write any complex ones of these, because they end up being resource hogs that tend to be tough to performance tune. Well, why is that? Well, part of that is just the nature of the way that a SQL server works. You know, SQL servers use B trees under the cover to basically be able to store and index their data. And B trees are very, very good at indexing data and being able to retrieve that data efficiently. They're not necessarily as good at being able to find connections between data. Graph databases, on the other hand, use a data structure from graph theory known as an adjacency list. An adjacency list, basically, when it comes right down to it, is essentially a linked list saying this vertex is connected to this vertex via this edge. Well, that data structure allows for being able to quickly traverse edges from one vertex to another, which is basically, in the end, what a recursive query really wants to do. You're trying to recurse across these connections in order to find your data. So if you want to look at a simple example, let's look at an employee hierarchy. Well, if you have the employee hierarchy, it's going to look something like this. And I want to maybe say, I want to find out how what is the reporting path from myself down there in the bottom corner to the CEO? Well, if I'm going to do it in SQL, it's going to end up looking something like this. This is, not necessarily the most fun to read, not necessarily the most fun to figure out, and probably not necessarily going to be the most performant option. So if I wanted to do it in graph, it looks like this. The query ends up being significantly simpler to look at. What you're looking at here is one of the graph query languages that's out there called Gremlin. We'll talk about that here in a minute. And then, to be honest, about half of that Gremlin query is really just being able to format the data to come out in the way you want. The other one I wanted to talk about is to be able to, an example of when you can do something in a graph database that's not easily done in others. But this brings us to the kind of concept of a path. A path in a graph database is a pretty unique data structure, because a path in a graph database not only says that two things are connected, but it gives you the sequence of vertices and edges you need to go across in order to get from one to another. So in this example, if we wanted to find the path from Alice to Bob, there's actually two paths. The first path is the red arrow. So there would be a path from Alice, and then that red arrow that says follows to Bob. There would also be a second path, which would be from Alice across that follows edge to Ted, and across that follows edge back to Bob. So that's basically what a path is. But how do you use it? Well, I like to use this riddle of the river crossing problem. I don't know if that's common. This river crossing problem is common here in Europe, but it is in the US. So the river crossing problem is you have a farmer that's got a fox, a goat, and some carrots. He can only take one of them across a river at a specific time, but there's a couple of constraints. He can't leave the fox with the goat, because if you leave a fox with the goat, that goat's going to be eaten. He can't leave the goat with the carrots for the same reason. If you leave the goat with the carrots, that goat's going to be eaten. So what it comes down to is it comes down to a constraint problem. You end up with, a current state where everything's on one side of the river, where you have three potential state changes you can go across. You can bring across the goat, in which case you're at a valid state. And you bring across the carrots, you're in an invalid state. Or if you bring across the fox, you're in an invalid state. So this is one example where as far as to do this in a sequel, this is not exactly an easy thing to do. Constraint optimization problems are definitely not something that are a lot of fun to try and handle in most existing technologies. There's a lot of brute force that has to go into trying to make those work. So what if your database could help you solve these problems? Well, a graph database can help you solve these sorts of problems by this. So to model this, what we'd do is we'd start out by modeling the current state of everything inside our graph. Just for this example, the T stands for the boat, the F stands for the fox, the G stands for the goat, and the C stands for the carrots. And the underscore is which side of the river it's on. It's going to get a little confusing, but can't make it too big and still fit it all on a slide sort of problem. So you end up modeling that. So you end up with an initial state modeled as a vertex. Well, the next step is to model all your state changes. Well, you can model your state changes as the relationship between a current state and a future state. So if you do this case, you can model those three potential state changes, and you'll see that if you take the carrots, it's going to lead you to an invalid state, which I've colored here in red. If you take the goose, it's going to lead you to a valid state, and if you take the fox, it's going to lead you to an invalid state. So now you take that and you do the same thing again, and you just repeat this, and I end up with two options. I can either take the goose back on the boat, in which case I return back to a previous state, or I can return empty, in which case I move to a new state. If I do this for all of the potential options, I end up with a graph that looks like this. So if I take a look at this graph, and I want to figure out how to actually answer the question. Well, to do that, I'm going to simplify it down a little bit. I'm going to take out any of the invalid edges, or any of the edges that lead to an invalid state, because we know we can't get there. And I'm going to take any of the edges out that basically return back to a previous state, because then you're just going to end up in a cycle inside of a graph. When I do that, I get this. Well, this comes down to, I think we can all pretty much easily see that there's two potential paths through this graph. Well, how do I query it if I want to answer this question? If I want to answer this question, this is all I have to do to be able to answer this. So this is an example where I run the query like this, and then I can get my results back out like this. So what you'll notice is a couple of things. One, it was a pretty easy query in a graph database to be able to answer a constraint type problem. And second, that not only do I get that these two things are related or that there's two paths, but I get how those two things are related. What is the series of steps I have to do to get from one state, from a desired state to an end state? Well, this is just a riddle. This doesn't seem like a real life problem, but I've used this same concept before to handle supply chain optimization problems. Maybe you have a set of warehouses and a set of deliveries that need to be made to a set of stores. Well, there's going to be multiple different ways you can actually do this. Well, if you model it as a graph, you can come up, especially if you model it as a graph and you put weights on the different potential options. Maybe you prefer to ship it via rail versus via truck, or via plane versus via rail. You can come up with essentially a set of weighted options that tells you what are the potential solutions to your problem. What are the potential solutions to a constraint type problem? And it's something I've actually seen used pretty effectively to be able to model these sorts of what if scenarios, because while it may not give you just the one answer, but it will present your users with a variety of options that they can use in order to say, yeah, I want to go with option B, not option C or an option A. So how do you know? How do you know if you have a graph problem? I like to look at these kind of 4 questions, and they're basically ranked in order of importance as far as I'm concerned, with the most important one being at the top. The most important question is really, do you care about the relationships between entities more than the entities themselves? If you do, that's usually a really classically good example of a problem that a graph database is likely to help you be able to solve. The second one is if you were to model this in a relational system, is it going to take multiple joins or recursive CTEs in order to answer it? Well, the reason this question is in there is basically, in my experience, if you need to do this sort of complex modeling where you need to do multiple joins and you need to do recursive CTEs inside a relational database to do it, that tends to lead to the fact that you really care more about how the data is connected than the actual entities itself, because you're doing that multiple join and that recursion in order to traverse the connections between them, in order to migrate across those different connections. Is your data and your questions continuously evolving? One of the features that we mentioned a little bit earlier is the flexibility of graph databases, the flexibility of them to not only answer different questions, to look at data in different ways, but also to be able to query them in multiple different ways that aren't necessarily, that are a little more flexible than some of the ways that you can query relational databases. And last, which is probably to me the weakest of these questions, is your domain a natural fit for a graph? If your domain that you're working in is a natural fit for a graph, just because it's a natural fit for a graph, if the questions you're asking aren't a natural fit for a graph, then it isn't probably a good graph use case. But if it is in one of those good use cases we talked about, it may lead you towards looking at that question a little bit more, or that use case a little bit more, to really see if you're actually just missing something. So where to start? Where do you start when you're going to go build something on a graph database? Well, if you start like me and pretty much everybody else in the world, you Google it. And if you Google graph database vendors, you have a problem. It's really confusing because the graph database landscape is growing, it's huge, and it's confusing. Specifically, so this slide was actually made by a graph consulting company earlier this year called GraphAware. And it's out of date already. It was out of date when they published it, but even since I put it on this slide about 2 weeks ago, I know of at least 2 new graph databases that have come on the market since then. So it's really hard to know where to even start because there's so many options. The graph database space, especially when you compare it to a lot of the other NoSQL database spaces, is very immature, and especially if you compare it to a relational database space. It's very immature. There's not a lot of standards out there. There isn't, a clear set of winners or a clear set of losers. So what I like to do is I try to bucket things into I'm a lumper. I like to try to lump things together to at least give me a place to start looking. Well, I kind of came up with 3 different buckets that I tend to look at these tools at. And the first one being, it's a graph computing engine. So when I think of something as a graph computing engine, what it really comes down to is it's a library. It's a library that I bring into my code, into my project to work with. Mainly, the main feature I see that puts it into this versus a database per se is that really these sorts of frameworks and features only handle data processing. They don't handle the persistence of the data. They're not there to basically store the data and retrieve the data. They're just there to run graph algorithms on top of the data. This means you have to use something like a relational database or CSVs or some other data source to populate that up, run your algorithms on, potentially store the data back into. And this is really optimized for a couple of use cases. And the big use cases are things like I want to run background processes on graph data. This is a great use case. You don't necessarily have to bring a whole bunch of new infrastructure in. You can just add it into a project you're working on, and you're good to go. And these are also really good for processing what are known as global graph properties. Global graph properties are the types of properties around a graph, something like centrality or influence, that requires you to look at all or most all of the data in your graph in order to answer that question. The other common characteristic of this is these are usually built around other frameworks, and usually a lot of big data processing frameworks, something like Hadoop or Spark. These are usually built quite often. These are built to run on those or built into those to do these sorts of questions. The second one is really the first of the database types I think of, and that's the RDF triple store. So the RDF triple store is based on the semantic web. It's where it originally comes from. RDF stands for Resource Description Framework, and it is a W3C standard about how to describe data for interconnection. And it's based on this subject-object-predicate model. Couple unique characteristics of RDF triple stores that I always look for. So in RDF triple store, each property is going to be stored as a specific vertex in your graph. So if you had in a relational world, if you had a table that had 1 row of data and 4 columns, you would end up with 5 vertices in your graph with 4 edges connecting them. as the example kind of shows up here. We have a flight, there's a cost associated with it, a to, a from, and the amount of money. The second big feature of these, and actually where they derive a lot of their power, is they have what's known as an inference engine. So you put in these triples, and then you put in essentially rules about your data. So you can put in different rules about the data. This inference engine will then run on top of it and be able to create new relationships based on those rules. And that's really that's what these are really optimized for, is to be able to infer new relationships in data for things you didn't necessarily know you had. The second type of database is the one I use the most often, and that's what's known as a labeled property graph. These are probably, I would say, potentially, it depends on you ask, but they could be, they're probably the more popular one that's out there. Certainly if you Google this, is probably the first one you're going to come up with, are the labeled property graphs. And these are based on vertices, edges, and properties. These are probably the most similar to a relational database of any of these, the concepts. So you have vertices, which represent the entities in your data. You have edges, which represent the relationships, and then you have properties, and those properties represent the attributes on your data. And those properties are stored as key value pairs on top of both vertices and edges. That's one of the distinct differences between a relational database and a graph database, is the ability for those edges to have rich metadata associated with them themselves. I like to think of them as in a graph database, relationships are first-class citizens, just like the vertices are. And these really come down to, labeled property graphs are really optimized for traversing known relationships. They're really optimized for being able to traverse across patterns of data, or patterns in your graph that you already know exist. So if you want to deal with inference more, you go towards the RDF side. If you want to deal towards traversals more, I find the labeled property graphs to be a little more better answer. But unfortunately, just like everything else in the world, the buckets aren't as clean as one would hope. You end up with an overlapping Venn diagram of how these things work. I mean, I work for DataStax, and even DataStax Enterprise Graph, the one that I work with all the time, it's both a computing engine and a labeled property graph. So that there's not as necessarily as clean a distinction as one would hope between the different types of databases. So it does get very confusing. But what's even more confusing is query languages. One of the things I attribute to some of the immaturity in the space is the fact that there isn't a single query language for graph databases. There's many query languages for graph databases, and many graph databases support more than one query language. So it gets very complex. There is an effort undergoing right now to try and standardize query languages, especially across labeled property graphs. But at best, it's going through ISO. It's just starting the ISO process, so it's going to be several years before there's really any solid agreement on what's going on. So this is another confusion. But what it really comes down to is, if you choose your database, that will really dictate the query language you can use. But before you run away, if I haven't scared you off yet, I'm glad. Before you run away, let's talk about my mistakes a little bit. Hopefully you can learn from my mistakes so you don't repeat them. And the first mistake that I've made before, and I see customers make all the time, is really understand what you're looking for in your data. One of the things that people will do is they'll put all their information in a graph, and then all of a sudden just somehow think magic's going to happen and they're going to get insight back out. You still have to know what questions you want to ask. You have to understand what that question means. Is that question going, is that question going to take is that question going to require that you to look at all the data in your graph? Well, if it's going to require you to look at all the data in your graph to answer this question, you're probably not going to get a response back in 20 or 30 milliseconds. And they say, yeah, you laugh, but I've seen people definitely think that that's the case. On the other hand, is it going to look at a really small subset, which is known as a subgraph of your data, in which case you might be able to get responses back very quickly. So really understand what it is you're looking for and what that question you're asking takes to actually be able to answer is one of the areas where I've seen people trip up frequently. The second one is understand what your tool is doing. I mean, this looks like a harmless little query, doesn't it? This looks like what you probably would write, right after the first time you try to do it. Well, this is the equivalent SQL to do it, which, for those of you that can't see, What you have to do is, so what that query is doing is it's getting a count of every vertex in a graph. So what you'd have to do, the equivalent SQL would basically be to create a temporary table, then loop over every table in your relational database, find the count of it, insert it into a temporary table, and then do a sum on that. Who's going to run that in production? Whose DBA is not going to kill them for running that on the production system? But I've seen people run that graph query on a production system and wonder why the graph slows down to a halt. So really understanding what it is that you're actually asking of the tool is really important. Next, understand what your algorithm is that you're doing. Well, there's lots of different graph algorithms out there, and there's lots of interesting things you can do with them. I mean, if you wanted to do something like a vertex or an edge lookup, that's a linear time question. That's a very quick thing. If you want to do a degree or the number of edges associated with a vertex, that's also a pretty quick thing. But you know what? Those don't tend to be the most interesting things you want to do with a graph, because you can do those with a relational database or a key value database or any other database out there. You want to start looking at some of the interesting things you can do with a graph. They start getting complex, or start to get computationally complex. You want to look at a shortest path algorithm, or what is the shortest path between two vertices in our graph? Well, that's at the best case is an O to the n squared. You want to do a page rank, so that the famous influence algorithm that Google created. You want to run that on a graph? That's an O to the n plus m, with n and m being the number of vertices and edges. So you quickly see if you try to run a page rank on a billion vertex graph, it's not going to be very quick. It's going to take a lot of computation in order to answer that. You want to look at something like a chromatic number, which if you don't know what a chromatic number is, that's a really interesting graph thing. Unfortunately, don't have time to go into it today. Or an all-pass algorithm. You're talking about NP-hard and NP-complete problems. I've worked with customers that have said, I want to run an all-pass algorithm and I want it to return on a billion-node graph and I want it to return in seconds. Well, that's just not realistic. So understanding what your algorithm is going to do and how complex it is really important to be able to set realistic expectations. Second one is, or the next one is, understand your data. We work with customers all the time that don't take the time to really understand what the complexity is within the data they're trying to work on. The one that kind of tends to bite you all the time in a graph is what's known as branching factor. So the branching factor of a graph is the number of successors for any node. So if you have a branching factor of 2, that means one node, if you traverse out an edge, it'll be 2 nodes, and then it'll be 4 nodes. Branching factor of 3 is 1 to 3 to 9. Branching factor of 4 is 1 to 4 to 16. Which doesn't seem like a big deal until you start saying, maybe my data doesn't have a branching factor of 2, it's got a branching factor of 6. Well, if you want to do a branching factor of 6 and you want to go out 6 levels deep, that means you're touching something like 56,000 vertices in order to get there. It's a very complex problem. So understanding what your data looks like is really critical in order to be able to, yet again, set realistic expectations of what you can do. The other part of understanding your data is understand what the tails are. Understand what the tails of your distribution are and how frequent those are. We were working with one customer where most of their data was fine. Most of their customers had no problem. However, they were trying to do, a lookup on an address. That lookup on the address for a couple of specific customers had 50,000 edges associated with it. So there's 50,000 people associated with a specific address. The data was actually valid, because my first thought was like everybody else here who winced was like, that doesn't seem right. It was actually valid. But, being able to understand that that was a problem and being able to mitigate that up front would have been something that would have helped, because it ended up being, it wasn't until we got to testing and testing on real data that we finally ran into that sort of problem. If this all just seems too complicated, don't worry, there are ways you can be successful with your graph project. I know, I asked that question earlier and there weren't many hands that got raised as far as who had successful graph projects, but there are successful ways to do it. So how can you be successful? Well, the first way is be prepared to think different. Don't think that you can take your relational methodology of how you think about a problem for a relational database and just apply it to a graph and it's going to work. There's a fundamental mind shift you have to take when you're going from a relational database mindset to a graph database mindset. In a relational database mindset, relational databases are based on set theory. And when they're based on set theory, they really have an entity-first thought about how you look at your data and how you model your data. You really think, what are the things in my data? And then you figure out how things are related. In a graph database, it's based on graph theory, and graph theory is all about relationships. So you have to kind of transform over to having a relationship-first mindset. You have to really start thinking about the relationships in your data more than you think about the entities in your data. Because graphs are all about relationships, and the relationships are what's important. If the relationships aren't what's important, don't use a graph database, is my advice. Be prepared that the tooling isn't going to be what you want. There's no such thing as a link to graph. There's no, the tools are immature. The tooling is not going to be what you want. It's not what you're used to from working with the relational databases. It's getting there, it's improving, but it's young. Relational databases have had 30 or 40 years to figure out all the different flaws and features. Graph databases in realistic terms have been around maybe 8. So they still have a lot of growing to do in order to actually get to the point where we have the same level of seamless tooling. So it's not going to be a seamless transition if you're trying to work with a graph database. Second is choose the right tool. I mean, who thinks that's the right way to use a drill press? I'm actually impressed that guy can hold it up. Choosing a tool just because it's available is dangerous. We've all done this, myself included. We've used a relational database because it's there, or we've used a graph database because it's there. But my experience, especially when you start getting with any complex sort of problem or any complex sort of data layer, is there's usually multiple different shapes of data you need to be able to handle. You need to be able to handle key value data pairs. You need to be able to handle relational. You need to handle a graph. And you need to be able to choose the right tool to solve the part of the job that you're working on. It adds some complexity in as much as now you have different problems you have to solve with data being stored in different areas and two-phase commits and all those things nobody really likes to talk about. But when it comes down to it, in my experience, it's still usually the right way to approach most of the problems because you introduce certain problems, but you solve other problems. Working in bite-sized chunks. This is one that shouldn't need to be said, but seems to always get forgotten in pretty much every graph project. I mean, who wants to start using new technology and all of a sudden try to do everything with it? Well, that's what people constantly want to do in graph databases. So don't try to boil the ocean. You use common sense. Just start with a small project, a specific silo of a project, and just use it to develop a reusable pattern. Don't try and say, I'm going to rewrite this entire application on a graph, even though you've never built anything on a graph in your life. It's probably not going to be a successful way to look at a problem. And then play out for failure. Like any new technology, you're not going to get it right the first time. These aren't necessarily this isn't necessarily the easiest transition that you have to make. Not only is it an infrastructure transition, it's a query language transition, it's a mindset transition, it's an operational transition. Assuming you're going to get that all right the very first time isn't going to happen. So plan in time for experimentation. Plan in time to make sure that you can get this right and have a backup plan because you know what? More often than not, I've had to pull the ripcord on it and actually go with a backup plan than I should say I've had to do that more often than I've liked to admit because there were just ended up being too many complications with trying to go down this route. So watch for the warning signs. This is some examples of some of the warning signs that I look for on projects that I've either experienced personally or I've worked with clients or colleagues have worked with clients that have run into. Bad warning signs. Choosing as a graph is the solution before you understand the problem. This is very interesting because I was actually in a ML talk this morning where she said the exact same thing. She doesn't want to go into projects where they've already decided they need to use machine learning to solve it because how do you know you need to use machine learning to solve it if you don't know what the problem is? Make sure you understand the business problem and then evaluate whether a graph's the right tool. Writing your own graph database and framework. While there are a few companies out there that are smart enough to write their own graph database and framework, most aren't. Most people don't have the time or the expertise to be able to go and write their own graph database and framework. So use the ones that are out there. Those ones have been tested. Those ones have been tested by multiple different people in multiple different scenarios, and they've already run into all the problems that you would run into. So just use one of them. Going back to what I said just a minute ago, is trying to do a complete rewrite of everything just using a graph. Just saying, oh, all of a sudden, we're just going to use a graph for everything because now graphs are cool and they're fun and we want to use them. Overconfidence in your graph abilities. I've never built on a graph database before, but I'm sure I'll get it right the first time. These are the sort of projects you just want to run away from. Run as fast as you can. Yellow light projects. These are ones where the project may be okay, but we're not sure yet. These are the ones where there's been little to understanding of the chosen tool. They've decided that they're going to use this because it was the first thing that came up on Google. This is the first answer that came up on Google, so we're just going to use that one to solve all our problems. We're not going to do the work required to figure out if it's the right tool for the problem. Nobody on your team has any graph experience. Nobody's ever tried to use a graph database before, but you're going to do it. Lack of schema enforcement. I didn't really mention this before, but one of the things that most graph databases have is schema. Well, not all graph databases have is schema. Some graph databases explicitly define schema, much like a relational database, in which case schema enforcement's pretty easy. Schema enforcement's done at the database level. You can't add a property to a vertex that doesn't exist. On the other hand, there's a lot of them when you do the research, because essentially properties are key value pairs, they're called schemaless. So they allow queries to add whatever properties they want to a graph as they're going through, or whatever labels, whatever they're looking for. This tends to be a problem though, because if you all of a sudden have five different properties being added to different parts of the graph with different names because different developers are choosing it, this tends to be, you end up with something that's first name and full name and last name, and they're spelled differently, and they all show up as different key pairs. So now your queries to be able to pull back realistic or reasonable data become horrendous. So you need to enforce the schema. If it's not explicitly done at the database level, then you need to implicitly do it at the application level. And the other one, which I've personally experienced, is working on projects when you don't have ops or DevOps support. Your ops and anybody in ops and DevOps needs to be brought into this process as early as possible in order for that to be successful. Because if you don't, much like you, it's a new tool they need to learn. They need to be brought up to speed on how this is going to affect their day-to-day workflow, how they're going to need to be able to manage this and handle it going forward. So you need to bring these in. You need to bring them in as early as possible in order to be successful. These are the projects where they're just kind of teetering on the edge. You can still pull them back to be successful, or you cannot. And then there's the projects we all want to be on. These are the ones, unfortunately, the rare few, but these are the ones where they're starting small. You're spending time, you're choosing the right tool, you're building in time for the team to learn. Because it's a learning process. We're all developers, we all love to learn. So, that's why we're all here, right? So we all want to learn. And these are the ones that have the plan for failure. They have the executive buy-in to know that this may not work, so we may have to fall back to a different way of solving the same problem. These are the ones we all really want to be on, and these are the ones where we love to get to. So if I haven't scared you away so far, and you want to get started with a graph database, I got a few suggestions. First, if you have an afternoon. You can go download, DataStax just released this tool, DataStax Desktop. It's still in experimental mode, but it works. Basically, you can go download it, and within a minute or two, you'll be up and running in a Dockerized environment containing our database and our IDE tool, which is a web-based tool. You can go in there. You can click on Explore Traversals with DSE Graph, and you can start getting work. You can start working away with graphs very, very quickly. Have some fun, learn some Gremlin. As my one friend said, you do this on a Friday afternoon, open a bottle of wine, and by the end of the afternoon, one of the two things will be finished. You'll either be done with your traversals or you'll be done with your wine. Either way, you've had a good afternoon. If you have a few days, find some of your own data. Load it up. CSVs are pretty easy to get into most graph databases. Load them up. Start writing some of your own traversals. Start taking some of the information you've learned and find something interesting. Maybe start running some of those recursive and pathfinding queries. See what you can find in your data. Maybe run some analytics on that. Find some distributions. Find what your data looks like inside a graph to be able to start down that path. If you have a couple of weeks to play around, you're pretty lucky, but sometimes people get it. But this is where you can start really digging in. This is where you can start spending time learning the text. Start not just learning the high level of what graphs are, how graphs work, but start learning of some of the underlying features and functionality of graphs, how they work, how they store data, when to use them, when not to use them. The other thing I've seen work very successfully for people is take this time, solve a problem that has business value. Run some graph analytics, find some clusters influence, maybe find some of those hidden insights that are not necessarily available to your business right now. If you have time, build a sample application. I've actually successfully seen people do this where they've been able to present this to management, and it's actually gotten them promotions, raises, and things of that nature because they were able to actually show the value of what they were doing. They weren't just sitting there playing; they were able to show the value behind what they were doing. So, summarize. Graphs are optimized to deal with highly connected data types. Connections in the data are where it matters for graphs. And they're able to use this to help provide insight into information in your data, specifically information in the connections in your data that can't easily be seen in other ways. But be careful, because working with graph projects requires a different mindset, and you need to approach it a little different than you're used to in order to be successful. So, kind of conclusions. I think graphs are great for two main reasons. First one is they're great for solving problems you can't necessarily solve with existing tech. This is the river crossing problem. These are the sorts of constraint problem, this constraint optimization problems that you can't easily do with existing tech that stands out there today. The second one is to be able to solve problems you can solve today, but differently and maybe more optimally. This is the whole hierarchy or recursive sort of scenario. But I do leave it as one last word of warning. They aren't magic. Don't think you can throw data in a graph and all of a sudden everything's going to be perfect. Make sure you have the right problem to fit them. Hopefully this talk's given you a bit of a guide as to what some of the right problems are and some of the things to look for. Last thing I'd ask you, if you want to, please follow me on Twitter. Also, buy my book, the shameless plug for purchasing my book. That's the link right there. And actually, that code underneath there, I think is good for another week. And that's good for, I believe, any Manning book. It's 40% off any Manning book, not just my book. So maybe if you're not interested so much in my book, but you want to read a book by any of the other Manning authors here or on any other subjects, please feel free to go out and use it. Lastly, I think I have a couple of minutes left. Are there any questions? Yeah.
How do you scale the graph databases?
So the question was, how do you scale graph databases? Well, how you scale graph databases sort of depends on which graph database you choose. For example, I work for DataStax Enterprise Graph, and ours is by its very nature a linear scalable graph database because it's built on top of Cassandra. So it's already built on a distributed foundation.
So imagine that there is a new big data set which is highly coupled. So this built on top of Cassandra. Then how this data is distributed across the market nodes?
So the question was, and specifically on Cassandra, since that's the one I brought up, was how do you partition the data out and shard the data out in a way that actually works for graph databases? Is that a fair? Okay, just make sure I summarized it correctly. Well, the answer is that comes down to a lot of data modeling that you have to do. And specifically in Cassandra, there's a thing called the partition key that you have to work on, basically figuring out the most optimal way to be able to cluster those data that you're going to request or you're going to traverse together into a single node or a single set of nodes. It actually becomes a bit, when you start talking about distributing, just like when you start talking about distributing any database, there becomes a lot of data modeling questions and data modeling trade-offs you have to make.
Yeah, but as I understand, the user needs to choose this primary partition key by itself.
Yeah, so for specifically, I'll mention specifically in DataStax Enterprise, what you have to do is when you create, DataStax has explicit schema. And when you create that explicit schema, you specify what field you're going to partition on. That data is then partitioned under the covers. You can still traverse across partitions, but obviously if you're traversing across network hops, it's obviously going to be slower than if you're traversing inside the same memory space. Any other questions? Yes. Yes. So the statement was, what I said was that both nodes and edges can have properties attached to it.
Yeah. So for instance, with this flight example, you had the nodes were the cities and the edge was the flight. And my question is, how do you decide what should be represented as a node and what should be represented as an edge? Because suddenly, perhaps you want to have pilots on that flight, and then.
Yeah, no, that's actually a very very good question. The question was, how do you decide what is represented as a node, what is represented as an edge? What represents a node and an edge is a little bit easier than what represents a property or a vertex. So usually when you do data modeling for a graph, specifically for labeled property graphs, you tend to think of the vertices represent the nouns in your data model, and the edges represent the verbs. So the actions tend to represent the relationships between things. So like flight to in this case would be the verb between those two. Now, where you put properties and what becomes a property and what becomes a vertex is actually a very complex thing. And usually that comes down to how are you going to query the data? Because you can put everything out as a property, or you can put everything usually either as a property or as a vertex. So for example, pilots. You could have pilots as both a property on the flight too, or you could have it as a vertex. It really comes down to how you're going to query that data back out in order to kind of know that. The other thing you can do, which is really common, is you put it in both places. You end up denormalizing a lot in graphs. It's not the optimal way to do it from a graph theory perspective, but it does end up being the pragmatic answer that you have to do, much like, everybody, third normal form would be great in relational databases, but how many relational databases only have third normal form? So does that answer your question a little bit? Yeah, I mean, the answer is it's hard. There's not a simple 2-minute answer. If you want, feel free to hit me up afterwards. We can talk about it in more depth if you want. Any other questions? Right. Well, thank you everyone for coming to my talk. Thanks to NDC Oslo for having me.